All right, so now we're going to talk about quadratic regression. There's not a whole lot of new stuff to this. If you watched the linear regression, you got basically the most understanding of regression there is. We're just going to be looking at a different type, which is just another, just pretty much the same thing in terms of typing in the calculator with one slight difference. But yeah, let's jump into it. So recall that you can use differences to analyze patterns in data. This is more, I don't know if we ever talked about this or if you talked about in Algebra 1, but how can you tell what a quadratic looks like without looking at the graph, but instead looking at the differences in the y values? So what this is saying is, focus your attention on this table here, right? All the x values are evenly spaced apart. You go -3 to -2 to -1 to 0, 1, 2, 3, right? All those are evenly spaced apart. Now look at the y values. You go from 9 to 4, which is subtracting 5, right? From 4 to 1, which is subtracting 3. From 1 to 0, which is subtracting 1. 0 to 1, which is adding 1, 1 to 4, which is adding 3, and 4 to 9, which is adding 5. And that's good. So those are the first differences. The first difference is, you're going down 5, down 3, down 1, up 3, up 5. So you can see -5, -3, -1, 1, 3, and 5 as your numbers. Now look at the second difference. Look at the numbers between those numbers. From -5 to -3 is +2. From -3 to -1 is +2. From -1 to +1 is +2. From 1 to 3 is +2. And from 3 to 5 is +2. So the second differences are consistent. They're all the exact same, right? So if you ever notice that about your table, that is the sign of a quadratic function. All quadratic functions will have those second differences match. So something just to be aware of, because one of the things we're going to get into later is, we're going to have all these types of regression: linear regression, quadratic regression, exponential regression, and you're not going to know which one's which, and that's going to make it difficult for you. But if you can find signs like this to help you understand what type of regression you're seeing, then you know how to go about, using your calculator. Because in your calculator, you're going to have to choose whether you want an equation that's linear, quadratic, exponential, etc. So if you look at your data, you can kind of make some determination as to whether it's quadratic or not or whatever. And if you notice this pattern, you'll know your regression is quadratic. So identifying quadratic data. We're just going to see if this data set is quadratic or not. So to do that, we're going to make sure that our x values are consistent. So you see 1 to 3 is +2, 3 to 5 is +2, 5 to 7 is +2, 7 to 9 is +2. So we just want to make sure that these are consistent. The x values are consistent. That's not what our focus is on, though. We just have to make sure they're consistent, though, because if they're not, then that skews what we look at for y. The x values are consistent, which is fine. I don't have to worry about them. Let me just now see if my y values make that pattern. So -1 to +1 would be adding 2. +1 to 7 would be adding 6. 7 to 17 would be adding 10. And 17 to 31 would be adding 14. So those are the first differences. But now I want to know what the difference is between those numbers. From 2 to 6, it's adding 4. From 6 to 10, it's adding 4. And from 10 to 14, it's adding 4. So since the second differences all match, that tells me that this table here is indeed quadratic. And that's something that's very useful for us to know. Now let's look at this one, right? Look at the x values, just make sure that they're consistent. 3 to 4, 5, 6, 7, right? They're all 1 apart, which is good. We have to make sure that those are all evenly apart. But now let's focus on our y's. Our y values, we're going 1 to 3, which is +2, 3 to 9, which is +6, 9 to 27, which is +5, 18, and then 27 to 81, which is just obnoxiously large. Can we just, anyway, I think it's, well, let's do the math. 54, I think. So those are the first differences. Now, the difference between that is 2 to 6 is plus 4. From 6 to 18 is plus 12. And from 18 to 54, well, it doesn't even matter. You can tell that the second differences are not the same. So if the second differences are not the same, this is not quadratic. So this is actually, and we'll talk about this in a future video, but this is actually an exponential function. We'll talk about how we can determine that later on, but this is not quadratic. We know it's not quadratic because we checked the second differences and we looked and noticed that the second differences do not match. So this is not quadratic. All right, look at this one. So again, check that the x's are consistent. 3 to 4 to 5 to 6 to 7. X values are 1 apart. Those are fine. Those are consistent. Now let's check the y values. That's going to be plus 10. This is going to be plus 14. 35 to 53 is plus 18. And then 53 to 75 is plus 22. Okay, so those are the first differences. Now let's check the differences between those. 10 to 14 is plus 4. 14 to 18 is plus 4. 18 to 22 is plus 4. So since they're all plus 4, the second differences are, that tells us that this is indeed quadratic. And then one more to check. Now look at the x values here. The x values, they're going down 10, 9, 8, 7, 6. But that's fine as long as they're spaced apart evenly. All of these are spaced apart one, by 1, which is fine. As long as they're evenly spaced apart, that's all that matters. But our focus is on y. On our y values, we have 6 to 8, which is plus 2, from 8 to 10, which is plus 2, from 10 to 12, which is plus 2, and from 12 to 14, which is plus 2. So you can see that all of these are already consistent. It's not the second differences that are consistent. The first differences are consistent. So because they are consistent, that actually tells us it's a linear equation, not a quadratic. So it's not quadratic, but it's good to know that if you see that pattern is linear. So that's cool, but not quadratic. Now, a quadratic model is a quadratic function that represents a real data set. Models are useful for making estimates. So just like a linear model before in the last video, represented a linear function, quadratic models will represent a quadratic function. And same thing with regression as well. Now, we noticed, we didn't really mention it, we kind of ignored it. But in the calculator, we got two values of R. We had regular R, which is known as our correlation coefficient, which we already talked about in the last video. So if you forgot what that is, go check that out. But now we kind of ignored, we didn't talk about what R squared was. So R squared is known as the coefficient of determination. This shows how well a quadratic function model fits the data. So it's basically like a regression for quadratic specifically. So the closer R squared is to 1, if R squared is 1 or really close to 1, it tells us our data fits a quadratic model pretty darn well. Which is very interesting for us to know. So R squared is just how well our data fits a quadratic function specifically. So now let's get into our calculator. Let's do some of the grunt work with that. So the table shows the cost of circular plastic wadding pools based on the pool's diameter, or wading pools. I'm not good at reading. Find the quadratic model for the cost of the pool given its diameter. Use the model to estimate the cost of the pool with a diameter of 8 feet. So basically, we have this information in this table. I need to find a quadratic model, which just means a quadratic equation. I need to find an equation that fits this data in my table, and then use that equation to estimate how much 8 feet diameter will cost. Well, the first thing is I need my equation, and my equation is going to be done simply in the calculator. So with the calculator, we are going to input these data points, this table, into our calculator. So we're going to go to Stat, we're going to Edit, and I'm going to clear my list that's already here. So to clear my list, I'm going to go arrow up to the top of the list part, hit Clear and Enter. So it deletes the entire list. Do that same thing here, Clear and Enter. And I'm going to type this in. I have 4, 5, 6, and 7 for my X values, and then 1995, 2025. I'm just going to type it in. Okay, give me a second. Okay, so I have my values typed in my calculator. So now to get my equation, I'm going to go to Stat, go over to Calc, and I'm going to choose my regression. Now, in the last video, we chose linear regression because we were doing linear models. But here we're doing quadratic models, so I am going to choose quadratic regression, which is this 5th option here. So hitting Enter on that. Again, X list should be list 1, Y list should be list 2. So we shouldn't have to worry about changing any of that. And here's our quadratic model. So we get my A value, my B value, and my C value, as well as my coefficient of determination, which is my R squared value. And I think that's all given on here, right? Yeah, so there it is again. So this is what I got on my calculator. So what that means is my equation, which looks like a quadratic, right? The A value is 2.41. We'll just round it a little bit. That's my A value, so 2.41 x squared. Then my B value is negative 21, so minus 21.56 x, because that was my B value. And then my C value is 67.64, 67.64, if we round it, right? So there's my equation, 2.41 x squared minus 21.56 x plus 67.64. And now look at the R squared value. The R squared value, 0.9998. That is super close to 1, which tells us that this is almost a perfect quadratic model. So that's very good to see that that value is as close to 1 as it is. Because if it's the closer you are to 1, the more perfect your quadratic is. So that is nearly perfect. But there's our equation. Okay, note that equation. So now, if we want to predict the value at 8, we can simply type in the 8 into our function. So if you go back to our function here, right, you can plug in 8 for the x, right, use those parentheses. Type that in the calculator and get an estimated value out. So if we go second mode just to quit, right, we can try that out. 2.41, 8 to the second power, minus 21.56 times 8, and then plus 67.64. 67.64. And it gets 49.4. So if we have a pool with a diameter of 8 feet, I don't remember if it was feet or not, but it would cost about $49 and whatever my calculator said, $49.40, right? Now this, obviously, it rounded it a little different, but they got very close to the same amount that we got. It's just going to depend on how much you round. So, of course, you can see that they rounded only 1 decimal place in their equation. We rounded 2 decimal places, but we got very similar results. So just be aware that rounding might cause you some differences, but yeah, it won't be too big a deal. If the problem specifically mentions what type of rounding to do, then do that type of rounding. So example 3 here. The table shows approximate run times for 16 millimeter films, given the diameter of the film on the reel. Find the quadratic model for the reel length, given the diameter of the film. Use the model to estimate the reel length for an 8-inch diameter film. Now this is interesting because of how many, I guess, variables it gives us. It gives us the diameter of the film, the length of the reel, and then how long that film actually is. So we're going to first find the regression between how the diameter of the reel and the length of the reel. So that's going to be plugging in these values for x and the reel length for y into our calculators. So if we do that, there's the results, but let me show you how to do that. Remember, you go to Stat, you go to Edit, and we're going to clear these lists, and you're going to type your table simply into those lists. So my table is here, right? So x values would be 5, 7. I'm just going to type it in, okay? Ignore me. All right, so with the table set up, we go to Stat, Calc, and we choose Quadratic Regression, and we get a quadratic equation for that data. And so that's the information that's displayed here. It's also on my calculator. It's the same exact thing. And you can see that the r-squared value, again, 0.996, very, very close to 1. So that means it's a very strong quadratic regression. So, but what the equation would look like, you would have y equals a is 14.3. So we'll say 14.3 x squared. B is negative 112, so minus 112.41 x. And then C is 430.11. So plus 430.11. So there's your equation. There you have it. So now if you want to find the value for x equals 8, does that even ask us that originally? Yeah. Use the model to estimate the reel length for an 8-inch diameter film. So if you have an 8-inch diameter film, how long would that reel length be? So you can plug in 8 as the x value, which means instead of having x squared, you plug in 8, right? And if you type that in the calculator, we'll save a little bit of time and just skip ahead. We get roughly 446. Is that centimeters or inches? I think it's inches. Feet. Okay, it's feet. I lied. 446 feet, roughly, in real length. So the quadratic model displayed here, which is the one that we found, where D is the diameter in inches, and LD, which is like, again, this is essentially the Y, and that's the X, is the real length for the diameter of 8 inches. The model estimates the real length to be 446. Yes, we know. All right, that's going to cover it. We'll save this for some other time. But that's going to cover it for quadratic regression. It's basically the same thing as linear regression. You still have to type in your data into the calculator, but instead of choosing linear regression, we chose quadratic regression. We got a quadratic equation, and we use that quadratic equation. So it's pretty much the same thing. So if you were lost at all in this video, please go back and watch the linear regression video. It basically walks you through the process in more detail. But if you already watched that video, this video should make a little more sense. All right, that's going to be it. I'll see you guys in the next video. All right, bye.